Dear all, I am Dr. V. Malati, Associate Professor at Department of ECE, SR University, Warangal. Today's lecture is on Advanced RISC Machine Architecture. Now, what is RISC? Reduced Instruction Set Computer. And it is ARM architecture. Example for ARM is Cortex-M. It's a 32-bit microcontroller Cortex-M processor architecture. It's a group of 32-bit RISC processor cores designed for energy-efficient embedded applications. For system-on-chip design and for embedded applications, this Cortex-M architecture is utilized. The key features are the use of separated data and program buses. Normally, there are two architectures in the computer. So, first one, Harvard architecture or one human architecture. In the Harvard architecture, the buses will be separate for data and program. That is, program means code or instruction. So what is the advantages of having separate buses for data and program? Normally in microcontrollers, 8051 microcontroller or 85 microprocessor, we do have address and data multiplexing. So the buses will not be separate for code and data. So address and data will be multiplexed in the buses. But here data bus separate, program bus separate. So that is why we are increasing the speed of the execution. It allows the parallel execution and a simplified pipeline for high performance and low power. And it does have the built-in NVIC. So NVIC means nested vectored interrupt controller. Why do we use NVIC? So there are special applications for NVIC. If we use, it causes efficient event handling. That means interrupts are handled efficiently, and it directs CPU controller to correct interrupt routine. So that means if an interrupt occurs, definitely the flow of instruction will be disturbed. So at that time, corresponding to the interrupt, the controller will move to the specific address location. So the NVIC is monitoring the CPU whether it is moving to the subroutine address correctly or not. Next one, core components and features. So first, regarding the RISC architecture. This architecture is based on RISC design which uses smaller set of simpler instruction. So there is a difference between CISC and RISC. CISC means complex instruction set computer. So in CISC, the instruction will be lengthier, and in one instruction there will be several tasks to be executed. But in case of RISC, since it is simpler, the instruction will have only one task to be executed. And second one, Harvard architecture. As I have already told you that the buses will be separate. So it uses separate buses for instruction and data, which allows for fetching the next instruction while executing the current one. It leads to the faster processing. So what is the meaning for this? The CPU no need to wait for the completion of execution for the current instruction. Even when it is in the processing, it can fetch the next instruction. An instruction set. It supports 32-bit instruction set, and often it supports 16-bit thumb instruction also. So if we use thumb instruction, 16-bit thumb instruction, the code density will be higher. And one more thing, wherever the memory usage is constrained, that is the availability of a large volume of memory, then we can use the 16-bit thumb instruction there. The 16-bit thumb instruction is a compact subset of 32-bit ARM instruction set designed to improve code density. So code density will be more and reduce the memory footprint. That means the memory availability may be reduced. If it is insufficient, then we can use thumb instruction definitely, and it achieves this by using 16-bit instruction. So what is the use of thumb instruction? Already we are mentioning it as 16-bit thumb instruction. So we are giving 16-bit instruction, but the architecture is 32-bit. Therefore, 16-bit to 32-bit conversion is happened. So, 32 to 16 means it is compression. 16 to 32 means it is decompression. So, while in the input side, it is decompression, and after performing the execution, the system will give out the output, and once again this will be compressed. So first one, decompression in input. In the output it is compression. So 32-bit output to 16-bit output, it is compressed. So that is the process of using 16-bit thumb instruction set. This allows for more instructions to be fetched from memory at a time, which can increase the performance on system with a 16-bit database. So what is the main application? So we are fetching the instruction before the completion of the previous, the current the instruction execution. That is why this causes the performance to be increased. So the performance of the system will be increased. And standard register setup. So in this case, what are the registers available in the architecture? It operates with the standard ARM register configuration, allowing easy switching between ARM and thumb modes via branch and exchange, that is BX instruction. So decompression in the input side, compression in the output side. How it is happening? So anyway, we are giving the 16-bit thumb instruction. This will be enabled by using the BX instruction. Once if we use BX instruction, then automatically we can understand that it is using the 16-bit thumb instruction. The processor can switch between ARM and thumb state using the BX instruction. So, BX instruction only enables the usage of 16-bit thumb instruction. That means 16 to 32-bit ARM instruction or 32-bit to 16-bit thumb instruction. Next, pipeline. It typically employs a simplified multi-stage pipeline to execute instructions. So now here, what is pipeline? As I have already told you that before completion of the current instruction, next instruction will be fetched. How it happens? We may think that the confusion will not occur. No, because the instruction itself is separated into various stages. For example, it may be divided into 3 phases or 3 stages, or depending on the architecture, it may go up to 6 stages in one one instruction. So suppose let us have the primary only. Suppose if the instruction is divided into three steps, three stages, then automatically what is the norm here? One task will be completed for one clock cycle. So in the same way, in the instruction, if suppose there are three phases, then automatically we have to supply three clock cycles. So three tasks will be completed in three tasks. But here in this case pipeline, since these stages are different, so one-to-one contact will not be there. They are independent phases. So one step, one instruction, three task. It is for instruction one. And in the second instruction, we assume that all are uniform instructions. So second instruction will also have three steps. So after completion, without the pipelining means in the clock cycle 4 only it has to start. But with the pipelining means we can start from here. So the first phase of the second instruction, it is the second phase of the first instruction. Both are literally different. They cannot coincide or overlap so that they won't create any confusion. So next second stage, third stage. Suppose three instructions we have. Third instruction, we can start the first stage of the third instruction here, because it is the third stage of first instruction, second stage of second instruction, first stage of third instruction. Both stages are independent, they are different, so that in one clock cycle, even if they enter, they won't mix, they won't give any error output. So there is no incorrectness in the output result, I mean outcome. So next one, third means 1, 1, 1. So finally, if 3 means separate, without pipelining, 9 clock cycles we need. But with pipelining, 1, 2, 3, 4, 5. 5 clock cycles only we need. In this way, we are reducing the number of clock cycles in the performance of the instruction by 9 to 5 means 4 clock cycles we have saved. Next one, built-in peripherals. The architecture includes integrated peripherals such as timers, so it is peripherals. So timers, watchdog timers, real-time clocks, and serial communication interfaces. So serial communication, as we know already, RS-232, for example, otherwise UART. UART means interrupt controller. The NDIC is a key feature for handling interrupt efficiently and deterministically with support for multiple interrupt levels. So we have seen already about NDIC. It is mainly useful for handling the interrupts. Next one, advanced high performance bus. The Cortex architecture is utilizing AHB light bus. So what is AHB? Advanced high performance bus. And this AHB bus is used to increase the speed. That means we can use the buses are assumed to be high speed interconnect. They connect components like CPU, memory, and peripherals. So peripherals in terms of system on chip architecture, and then fast data flow. The usage of AHB will enable the fast flow of data. And then this bus architecture connects the core to memory and peripherals, optimizing for performance. And then low power design. The architecture includes features like sleep modes. So this is the special feature in Cortex architecture. So sleep mode means when the system is unused for long time, that means for certain after some certain duration of time, the system will become sleep mode. So sleep mode means it will not consume power. So in this way we can reduce the consumption of power when not in use. When the system is not in use, it will automatically go to the sleep mode after some time duration. That is set by the architecture. The basic block diagram of Cortex M3. It is Cortex M3 core. So it is processor core. And then debug system. So this debug system I will tell you in detail. So debugging is happening inside the processor component itself. And then internal bus. So debug system, in between Cortex and debug system, the flow is bidirectional. And from the internal bus, the unidirection connection will be there to Cortex M3. In the same way, the bus will be connected to the peripherals from the internal bus as well as to the memory. And clock and reset input output will be used separately. Then the Cortex M3 is a 32-bit microprocessor. So we know what are the basic processors. Starting from the 8-bit processor, it is Intel 8085, and then it is evaluated as microprocessor 8086. It is 16-bit processor. And then 8051 microcontroller, it is 8-bit, because the difference is it is inbuilt, it is having an inbuilt input output port and memory also. And then this 32-bit processor will come into effect by the Cortex M3 chip. It has 32-bit data path and 32-bit register bank. So all registers available in the processor is 32-bit only. That capacity of storage is 32-bit only. And 32-bit memory interfaces. 32-bit memory interfaces. The Cortex M3 offers many new features, including Thumb 2 instruction set. So Thumb 2 technology already I explained. It is the conversion of 16-bit to 32-bit instruction, and very low power consumption. This also it is due to the sleep mode property of the Cortex architecture, and the low interrupt latency. So it is due to the NVIC. It will go to the correct subroutine as well as the interrupt handling time will be very small. That is why low latency. Immediately it will be handled by the processor. That is why low latency. The delay in handling the interrupt after occurring, it will be less. And then LPC 1768. This microcontroller belongs to Cortex M3 core, and LPC 1768 is mixed signal processor. It is latest version from NXP Semiconductor. The processor has Harvard architecture. So Harvard architecture means we do have separate bus for data and code. Code means a program or instruction. This allows the instruction and data access take place at the same time. So no need to wait for multiplexing and no need to wait for the segregation of data from the address. Which one is address, which one is data, and for that also to indicate that separate pin will be there. These are all not coming into this. which results in higher performance. So automatically speed will be increased so that performance will be enhanced. And then, however, the instruction and data buses share same memory for complex application. So, very lengthy program and complicated task means necessary to use more memory storage. The volume of the memory will be more. At that time also it is able to handle. So that is why how it is handling means normally memory sharing is not, we are not talking about that, but whenever the task becomes complicated, then it permits the sharing of the memory. So data will be stored in the some part of that dedicated part of the memory, and remaining in the remaining part of the memory the program will be stored. So sharing is allowed in this case. That is the that is also a special property of this. Where more memory is primary need, the Cortex M3 processor has an optional memory protection unit. See, this is important, memory protection unit. This memory protection unit means because we are having the connection with the input-output peripherals. Suppose the peripheral is not authenticated and it tries to have the connection with the architecture, then it will identify, it will recognize. For that only MPU, that is memory protection unit, is used to protect the processor, that is protect the processor from the user, from the interruption by the unauthenticated peripherals. And then interrupt handling feature. So already we saw NVIC is specifically for handling the interrupt. The built-in NVIC reduce the interrupt request handling latency. So latency also we told, once if interrupt occurs, immediately it should be responded to by the processor. This shows the it is measured in terms of latency, low latency, and it allows to change the interrupt priority in runtime. So actually, so there are several interrupts that may request for the processor, not only one interrupt. There are several interrupts which may occur, and that too not one by one. We cannot expect every time. One or two or three they may occur simultaneously. If simultaneously occur, which one will be given preference, which one will be given service first or next or last, those will be decided by the processor. And at the sometimes like 8051, the order of the priority will be given to the interrupts. Suppose beyond that priority level, the Cortex architecture is able to change the priority of the interrupt, that too during the runtime when it is in execution, that during the processing time also it is able to change the priority order. So which one comes first, which one comes next, everything will be decided by the Cortex architecture only, and that too it is not uniform at all time. They may change depending on the requirement. The processor status or memory contents can be access driven when the core is running. So this is also another support. Next one, built-in support for 6 breakpoints. Now, what are the breakpoints? The breakpoints will be created in the instruction to check for the error, that is debugging purpose it is made, and 4 watch points. Optional embedded trace macro cell, that is ETM for instruction trace and data trace using data watch point trace, that is DWT. So both work in coordination with one another to debug. So this ETM beyond the breakpoints. So here we told there are 6 breakpoints possible. Beyond the breakpoints in JTAG, it provides a deep debugging insights. So for instruction tracing, it captures a program flow and branches and data access. It outputs via trace port. So these many operations are performed by ETM. That is why not only for debug, for several purposes, the ETM block is used in the Cortex architecture. And new debugging feature including fault status register, new fault acceptance, and flash patch operations which makes the debugging much easier. And one more block, instrumentation trace macro cell. This ITM, it is a built-in software, sorry, it is built-in hardware peripheral for advanced debugging. So for debugging, how many factors we are adopting? So debugging and ETM, DWT, breakpoint, watch point, these are all together used for the debugging purpose only. And and one more thing, it is used for advanced debugging without halting CPU. So CPU speed will not be reduced or intermittently it will not halt. So CPU operation will be continuously moving on. Therefore it is faster than UART. Universal asynchronous receive transmitter, that is the interface only, serial communication interface only. And minimum code overload. So for using this debugging, don't think that we have to use more code. So this code overhead is completely reduced, it is minimum only, and it allows software to send real-time event or data streams like print of messages. So it is a software only, entirely software only. And easy to use method to output debug information from test code. So output debug means it is printf. Then PC sampler and counters inside the DWT provide code profiling information. And one more thing, this point about the DWT, it is an optional debugger only. So if we want to use, we can use. Otherwise, we can keep it not in use. And it is a trace unit only, and it provides breakpoints on data access, and it generates trace events. So if we use DWT, DWT itself produces or generates some breakpoints inside the code. And then this is the main architecture of the Cortex M3 architecture. This is the memory. It is almost similar to the ARM architecture only block diagram. Memory interface and interrupt controller. That is the NVIC only, and instruction fetch unit, decoder. It is register bank 32-bit, ALU arithmetic logic unit. All are connected together with the memory interface. Trace interface, already I told you, it is used to debug. And then interrupts coming across the interrupt controller, and then instruction bus and it is data bus, both joining with the memory protection unit. It avoids the interruption by the unauthenticated user. And then bus interconnect, and then a debug interface, it is debug bidirectional. And from this bus interconnect bidirectional way to the code memory system, and peripherals and private peripherals also may be used, and it is optional only. Debug to the going to the output, it is optional only. And finally, what are the components inside? Anti-peripheral components of LPC 1768. It includes Ethernet MAC layer and USB, Universal System Bus Interface, that can be configured as either host, device, or OTG, 8-channel general purpose DMA, direct memory access controller, 4 UARTs, so serial communication interfaces, and 2 control area network channel, and 2 SSP controller, serial peripheral interface, and I2C integrated circuit interfaces, 2 input plus 2 output I2S surface and interface, 8 channel 12-bit A to ADC analog to digital conversion, digital to analog converter, motor control. It is for analog pulse width modulation, and quadrature encoder interface, 4 general purpose timers, 6 output general purpose PWM for analog input output matters, and then ultra low power RTC with separate battery supply, and up to 70 general purpose IO pins also. It supports the operating system like Windows, CE, Linux, Palm OS, and so on. And then, so it is normally ARM architecture supports the load and store instruction only. That is why it is called as load store architecture. The main memory instruction is load or store. So with the 3 basic type of instruction. Number 1, register to register operation. It is for processing data, and then memory operation which move data between memory and register, and third one, control flow operations enabling program language control flow such as if and while statement and procedure calls. So jump operation, otherwise a conditional program, then the controller has to transfer to some other memory location, disturbing the normal flow of instruction. So these 3 are the main basic types of instruction in case of Cortex M3 processor. Thank you.